Hi, and welcome to the first lecture of Environmental Geology. My name is Ken Neuhauser, and I'll be taking you through this course this semester. And if you have any questions, just contact me, and I'll be sure to take care of those questions, all right? First thing I want to do today is to talk a little bit about, kind of an outline, is some of the main things you need to remember about the course. And then after that, we'll go into a generality, because this is an introductory lecture, introduction to the course itself, and then our next session we'll get into some specific topics at that point. All right, so again, I want to kind of talk to you about what particular textbooks are being used for this class. And we're putting together kind of a combination of two different environmental type disaster textbooks out there. The first one's called Natural Disasters by Abbott. And the second one is by Montgomery, called Environmental Geology. And so what I've done is put together kind of a combination of these two texts, selected different chapters from each one, and we'll, as you'll see, put together a series of PowerPoints on these topics. The book that you'll purchase is put together by the publishers. It's part of the publishing company called Primus, and it's kind of a combination of the two. It's in black and white. You also can access the this text in color online via the web, and you can be able to get that email address off of the syllabus of the course, which is online with Blackboard. Now, this series is being put together by Fort Hays State CTELT. They're going to be generating these lectures and putting them to tape or whatever type of media for this course. All right, let's talk about what probably is more important to you, and that's going to be taking the quizzes and the exams. In this case, all these quizzes and exams will be on Blackboard. That means you need to access Fort Hays State's website, get online to the link with Blackboard, and I've got some subsequent slides coming up that will show you how you go through this process. All right, so the best thing would be to just log on to Fort Hays State's main page and go from there. The key thing about getting on there for you is once you get on here and access the course in Environmental Geology, this will be 340 CA, you'll want to click on the button that says Course Information, and this is where the syllabus is. Once you get to that site, be sure you print the whole syllabus off and check out what is expected in the class. All right, now here's what you're going to see when you first get on Fort Hays State's website. You will be, this page will look like this with a map to the campus, and where you need to focus is on the center left here, and that's the link to Blackboard. You simply click on that link, and when you'll do, you'll get this screen. And this screen is going to ask you to log on to the Blackboard system. Okay, so you'll go up here to the top left and click on Log On. And when you do that, it's going to ask you for a username and a password. Now, you'll be assigned a username and a password by Fort Hays State University when you're enrolled in the class. And once you put that in, you'll get to the Blackboard page. Now, this happens to be my personal access to the page. It shows me what classes I have and different types of tutorials. Your page won't look exactly like this, but it'll look similar. And then you'll want to log on to the specific class. In this case, it would be for the on-campus one here, on-campus 340 CA for the quizzes, and for the exams, if you're off-campus, it'll say off-campus. Of course, that statement's for reference to those people who will be taking this in the future through virtual college. Once you log on to the class, this is kind of the main screen now of this course. This happens to be for the quizzes. And up here in the top left is the button for course information. This is where practically everything is that you need to get into. And once you get on there, there'll be the syllabus. The chapter quizzes will be there. And the quizzes are on all semester, at least for this semester. And you'll need the password I gave you to log on to that. Okay? Has anyone here tried to do this yet at all? All right, now what will happen for the off-campus people in the future is that they will be emailed, okay, you're going to be emailed the particular passwords. And that will be sent to you through your SCATCAT account. So be sure you look at your SCATCAT account, not your personal yahoo.com or other type of personal email that you might use, Hotmail or Yahoo. Be sure to check out your SCATCAT account that the university assigns to you automatically. So that's kind of the sequence you need to get into that. All right, the rest of the course that you'll be working with is simply to follow along with the PowerPoints and take notes like you would in a regular lecture, and then review that material, log on and take the specified quizzes, and of course the exams. In this case, if you have any questions, you can email me. My email address is on the syllabus. That'd be the best way to get a hold of me. Okay, now it's note-taking time. All right, we're going to start out with some notes on environmental geology. What is environmental geology? What does it encompass? What do we look at? What are we concerned about in environmental? I mean, I think out in different parts of the world you see a lot of situations with polluted water. Is it all about the pollution problems that we have with water? What about earthquake destruction? You know, see earthquakes in California and in the Middle East, different parts, a lot of destruction with that. Is that what environmental geology is about? How about mine accidents or collapses or highways that collapse? Volcanoes when they erupt. The most recent biggie in our country, of course, is Mount St. Helens. But there's been volcanoes all over the world that erupt all the time. There's a lot of devastation with that. Is that what environmental geology is? We had hurricanes just this last fall on the East Coast, causing lots of damage. Fortunately, we had no big meteorite impacts recently, but that can happen. Is that environmental geology? Well, it's all of them. And of course, a lot more. And that's what we're going to go into in this class, is to cover these different topics and try to learn all the processes and see what we can do on our part to monitor it, keep an eye on it, collect data, and maybe predict and save lives in these cases. Now, all that we went through on the list, most of these are natural disasters, okay? Things as a result of geological processes, natural geologic processes. However, once in a while, we humans get in the way. Some things that we do and have done in the past cause disasters. Now, we want to introduce a new term here to you, anthropogenic. And you'll see that quite often throughout the term now, anthropogenic. That means human-induced problems, or human-induced. Some of our activities that we've done have caused disasters, mine disasters, collapses of structures, and so on. So let's just take a look at some of the images of these kind of things we've just talked about. We've put in our list, okay? A shot here of an earthquake in India just a few years back. And you can see, of course, from the collapse of the structures, the major problems. There was an earthquake just recently in the news I don't even have in the PowerPoint. So this is going on constantly. It's a constant dynamic system on the planet. So you may see pictures here from 1990s to 2000, but in the future, you're going to hear stuff in the news all the time that will affect you. Here's a quake-induced landslide in El Salvador. It's not so much that the building was shook and the structure collapsed on you. Here, a mass of material slides down a hill, a mudslide or a rock slide, and buries a community and kills people. Of course, sometimes we do have our toys, our cars, our buildings destroyed and smashed. Here we are in LA on the left. In Kobe, Japan, a city in Japan that felt that they really were earthquake prone. And they really designed the city around it, said, okay, I think we've got that covered. We get a major earthquake here in Kobe, nothing will happen. Nothing disastrous. Well, they were wrong. The earthquake was so strong, the type of vibration set up things, and they had a major disaster. A lot of people got killed. And one of the interesting things to look at, even in this picture, is of the fire. So as we go through this semester, we'll break these topics down. We'll look at individual chapters on earthquake activity here in the United States and around the world, and other types of disasters. Here's a rock fall that took place in Yosemite National Park in California not too long ago. Now, there's not a lot of people here. There were campers that got killed, a few people hiking along the trail, but the rocks broke loose and fell down. And we'll look at, well, what are the reasons? Why? What goes on here? What's happening? Why do these particular things take place? And of course, floods. Floods are natural, but floods, some things that we do. Anthropogenic situations where we've tried to have flood prevention in a certain locality causes a problem downstream, kind of displaces the problem. So floods can be disastrous. Of course, volcanoes, a number of great movies out recently about volcanic disasters and so on. But they're beautiful. You see new landforms being developed, but when you get to certain types of volcanoes, they can be extremely disruptive. Very, very explosive types. And we'll look at, why do we have mellow, quiet, nice to see, get right up to the front type volcanic activity, and others, you don't even want to be within miles of these places because the way they are so explosive. Here's that kind you don't want to be too close to at all. It's called a pyroclastic flow. We'll come back to this in detail later on in the course, but it's a very, hot gaseous cloud that comes blowing down the side of a volcano nearly 100 miles an hour or more. You can't run from that. You're going to get trapped and incinerated in it. This happens to be on the island of Montserrat in the Caribbean. Again, we'll look at some of these pictures. I just love this photograph. This is kind of a very interesting shot of a recent meteor streaking across the sky. Meteors are really cool, kind of unique to check out, but if the big ones hit, then we can have some big problems. And it'd be quite interesting to see where we can go with what these things mean to us as geologists and environmental geologists. I mean, sometimes these things can hit so hard, they'll actually vaporize the surface of the earth. They'll melt. The intense heat from the pressure impact will actually melt material at the surface of the earth, inject it into space. Sometimes it's just the debris goes into space and floats around. Other times it'll come back down in our gravitational pull and hit the earth. Up here on the top right, of course, is the crater in Arizona, meteor crater. In the bottom right is a digital elevation model of a meteor that hit at the end of the Cretaceous period about 65 million years ago on the Yucatan Peninsula. That white line running through there is the coastline. Right in here, this is land here, and this is in the Gulf of Mexico. So that thing hit right on the coastline. And what you're seeing here is a three-dimensional model done through geophysics of gravity data in that case. And you can see the circular impact. And this may have been one of the major things that helped really push the dinosaurs into extinction. We'll look at how these types of things may or may not have been involved in extinctions of life throughout time. When a meteor hits and blasts the surface of the earth like that, it can create all kinds of features. And again, we'll look at these in detail, but quite briefly in the bottom right, here we have some strange patterns in the rock. This is up in Sudbury, Ontario, in Canada. And you can see these strange kind of cone-like features here. Over on the left, this black material in here is actually melted rock that cooled off quickly and became a glass. The meteor's impact melted stuff in the crust of the earth. And here on the top, we see some of the other fragments that are produced by that pressure impact. Here we have some very strained crystals. These happen to be quartz crystals under a microscope. This is under a scanning electron microscope. And some of that glassy, melted material that's blasted up in the atmosphere cools off and becomes solid droplets and rains back down to the surface of the earth. And we can find these little things. Stuff here in the top right are some of these little glassy things called tektites. And we'll look at those in a separate chapter later on. So there's a lot of interesting clues that we find on the surface of the earth buried within the rocks that help us unravel ancient kind of environmental disasters as well. So this is chapter 1. This is kind of an introductory chapter in your Primus text. And this particular chapter focuses on some processes and cycles and energy sources for these processes. So this is chapter 1 in Abbott's textbook. It's titled Natural Disasters, Energy Sources. Feeling we've got some. I'm going to bring these all up right now. PowerPoint seems to have a little glitch, but that's all right. So why do we want to study environmental geology? We kind of know what it is now, but why do we study it? Well, as humans, probably the first thing is that people die every year. We have loss of our material things, our buildings, our highways, and so on are destroyed. So the human fatality aspect of it, we don't want that to happen. So is there anything we can do in our studies to kind of help with that, to mitigate it? Of course, money-wise, economic losses. If you lose something that you may not be insured, for one thing, and so you've got to pay for it yourself to rebuild. If you are insured, the insurance company pays, and of course insurance rates go up when these things happen. So hurricanes affect the insurance rates. Coastal hurricanes affect the insurance rates in the middle of the country. Earthquakes somewhere maybe in the central part of the country can affect insurance rates on the coast. So it's all tied together. As geologists, though, we really would like to understand the process. We want to see what's going on, get right up into the face of these disasters and study them. We want to collect as much data as we can, because if we get this data, we understand the process, then maybe we can use it to predict future disasters. At least attempt to predict. And our hope is to do what? To prevent those problems again, to prevent the human fatalities, to prevent loss to structures. So part of this goal, this process, we can lump under something called mitigation. A new term to your vocabulary now. Mitigation refers to the actions we do to eliminate, reduce, or prevent losses of some sort. Maybe it involves building special shock absorbers on high-rise structures in an earthquake-prone region. Or maybe with the way the engineers design another aspect to that structure. Maybe it's finding ways to divert areas where are flooded around main cities or something. So there's lots of mitigating things that we can do to kind of prevent these losses. What's litigation? Okay, litigation would be about the legal aspect. Who is at fault? Let me give you a goofy example. Let's say that a geologist like myself decides to make a prediction. I work for the USGS in Los Angeles, and I'm studying earthquake data, and I go, you know what? I see something in a pattern of things. Rates are changing, the data that I'm collecting, and I'm going to predict that next weekend will be a major 7.5 or 7.9 earthquake in Los Angeles. That would be disastrous. So I make that a news comment. I send it out to the media, and it's on the radio, it's on television, okay? And so now everybody else in the city has to come up with a plan. The mayor, okay? Somebody in charge of the zoo, somebody in charge of the fort, somebody in charge of the police, somebody in charge of the hospitals, schools, etc. Anybody in authority who says, we've got to take care of people to prevent losses, so maybe we're going to create an evacuation process. So we got a plan. We've already got it built in, and hey, that geologist, Neuhauser, said that there's going to be this biggie. Let's all get out of town. Let's evacuate everything that we can that's necessary. Some things cannot be evacuated. So everybody goes off someplace, like maybe some of you go off to Hawaii, some of you go off to Vegas. Okay, you leave your home, leave your business. Well, now you're in Vegas about a day or two, and the earthquake didn't come when it was predicted. Well, gee, now it's a week, and somebody has to make a decision. Are we going to let them back in? Can they come back home? Well, no, we better wait a little bit longer now. So now a month goes by. Well, what are you going to feel like? You're going to be a little upset. You're going to be kind of angry about that. And of course, you're going to have a loss to your business and so on. What if someone actually, kind of snuck back into your town there and looted your house or stole things? So who comes into play at this point in time? The lawyers. Okay? Somebody's going to get sued. And there's all kinds of examples of lawsuits over situations like this. particularly water issues. One of the big chapters we'll go into later on this semester, one of my pet peeves about water. Out here in western Kansas, water is extremely significant. And we'll see situations where Colorado's suing Kansas, and Kansas suing Colorado, and Kansas suing Nebraska, and back and forth. The United States, or Mexico being sued by, or the United States being sued by Mexico over water in the Colorado River. That's the litigation part of it. So studying environmental geology would be a good thing if you're going to go into law, to study environmental law. And this list of examples could go on and on. Okay, now I want to go into the geology and global changes, and I'm going to go through a list of things that are some of the observed changes we've seen in the environment in the past 100 years or so. Now the first one is about carbon dioxide. Atmospheric carbon dioxide concentrations have increased 29% since 1860. Now what may be the reasons for this carbon dioxide? Some people believe it has to do with the Industrial Revolution or belching out of burning of fossil fuels over time. Others believe it may be due to volcanic eruptions. So that's the importance of going out and collecting good data and coming back with that and analyze it and be able to distinguish between the two. The point, though, is that it's getting more and more into the atmosphere, which means we're going to have an increase in global warming because of it. Here's another bit of data on that. Okay, 50% of the world's wetlands have been lost in the last 100 years. That's a dramatic increase, certainly affecting the eco-community, the biology, the organisms that begin in the wetlands and, of course, are part of that food chain. Some of this loss is due to nature, but a lot of it has to do with humans, the anthropogenic changes of bulldozing in swamps to create new real estate. Atmospheric concentrations of methane have increased dramatically in this case in the last 200 years. Why? What's going on with that? Where's it coming from? Is it something we're doing? If you're a farmer, this is extremely important, or a rancher. Soil degradation. Soil degradation has affected 2/3 of the world's agricultural land in just the past 50 years. A lot of this degradation has to do with chemical pollutions. So we're going to look at some of these conditions later on as well. So things do change. They always have and they always will. And what we look for are the rates of changes. How quickly is it happening? And can we tie it to some very specific effect? Something that we're doing that we can alter and change? And if we can't change to it and adapt to it, then we as a species will have problems. And so in the long run, as part of the themes of this class, that's some of the stuff I'll bring up to you, is that you're going to hear a lot of science and have to learn a lot of terminology. But one thing I want to express to you as a class, okay, is that when you leave the class and you go into other parts, other disciplines, wherever you go, most of you will probably not become geology majors, but the decisions that you make, especially if they're important ones that affect these changes, you're going to play a major role in what happens to we as humans. Here's a table from the text, table 1.1. One thing I want to point out as I show you a lot of these tables, I don't expect you to memorize the data out of it. If something's really significant, a number, a specific event, I'll tell you to remember that, okay? But I just wanted to point out, it says the 16 deadliest natural disasters in 2001. And it goes from earthquakes, in this area floods, and there's some typhoons. But they're mostly of that type, aren't they? And look at some of the fatalities that were listed here, just in that short time period in 2001. A lot of loss of life. And these are even the small ones sometimes. 20,000 is not a big one. Here's something you need to remember, though. And you're going to live in different parts of the world. You're going to be close to these natural disasters. The two most disastrous processes are 1, earthquakes, and 2, hurricanes. Now, here's a list of disasters from 1947 to 1980, from quakes, tsunamis, volcanic eruptions, floods, hurricanes, tornadoes. other severe weather, landslides and avalanches, and you look at some of the numbers in these fatalities. Look at this, 354,000 for a quake in Asia. But the total in this time period is nearly 500,000 people. Take a look at the hurricanes. And the hurricane in the Asian region, nearly 500,000 already. In fact, if you look at that, nearly everything from that hurricane in one event. So that's one event. And so we want to look at, well, if you can focus in on which of the disasters are the worst, you can put most of your energy into studying those and try to help in those regions. Of course, one thing we're concerned about in the United States is money. It's going to have an effect. It has a ripple effect on our insurance costs. And this is a chart showing changes in costs from the 1950s up to 2000. And just look at that rise. It's beginning to rise rather rapidly in relationship to these disasters. So the United States, okay, having the most money in the world, in this case, we have, the most high or the highest insurance rate in the 20th century, and probably will continue to do so into the 21st century as other worlds come into this, but other countries come into this world process. But rising insurance costs, you have to pay those insurance rates. Now, maybe right now you're not. Your car insurance, okay? But when you purchase a home, you live in a certain region of the country, these are going to vary. Those rates will be based upon where you live. And something happens on the East Coast, like I said earlier, it'll have an effect here in Kansas, and so on. So we study these events. We try to categorize them. And one thing we do see in a pattern that develops is that big events are fairly rare. Meteorite impacts are really rare. So this chart shows us the frequency of how often they occur versus how big they are. And in plotting up those things of all the different categories, we see this nice straight curve that they are rarer. That's good, that we don't have major things happening all the time. That would definitely affect us as a species. The other thing is that they have this kind of larger return time that we can see as we look at this stuff. So big events have longer return periods. So we're looking at kind of what? Statistics, aren't we? Provides us with data to make predictions about what can happen. So say flood intervals. Insurance rates in certain areas are going to be based upon flood frequency. Now, 100-year flood, 25-year flood, and so on. So wherever you move to, think about it. Obviously, I think you're going to move to where your job takes you. But the other thing I can recommend to you is simply be aware of all of those places you go to. You move to Los Angeles, get yourself educated about where the safe places are, how you're going to evacuate yourself. They'll try to tell you to do it, but once in a while, you're going to get caught. And it happens, so check it out. So we get lots and lots of statistics. Here's another one of these tables in the textbook. Table 1.6 on the probability estimates for 10 in 1,000 death natural disasters. And it's like listening to football statistics. And I'm watching a game, whether it's golf or football or baseball or basketball, and something happens on the field, and all of a sudden they've got these statistics that are just, like, where'd they come up with that so instantly? They've got tables full of just, bam, they pull it up. It's very quick. We have the same thing for natural disasters around the country. So we're generating lots of statistics. So who uses these statistics? What are we doing with it? Well, I've already mentioned one, the insurance companies. What you pay is based upon how this works. City planners. Where's the best place to put a new division in the town? Where's the best place to build a hospital, a zoo, a highway? How does that work? There's lots of variables that come into play, and unfortunately, I think sometimes that natural disasters aren't always part of the formula. It's becoming more, they're becoming more and more aware of this as they do it. Okay, to plan a city and where to go and work that out. And we'll look at some examples of how they're doing this later on in land use planning. Engineers, they were probably early on to the bandwagon of doing this, designing buildings to resist earthquakes and different types of structures like dams or mines and so on. Or, from flood damage. How do we work with the structures that we live with in natural disasters. And us as geologists, of course, we want to know it for purely academic reasons as well. We want to unravel the story of the Earth and figure out how it ticks. All right, Abbott goes into a segment now in his textbook on disasters here. Like, where do these things get their energy from? So what are the energy sources, the driving mechanisms for all of this? Well, we're going to look at it two ways. We're going to look at it from an external source and an internal source. Let's take a look at the external energy sources first. First of all, and particularly in the earliest phases of the Earth, as celestial material was pulling together under the force of gravity and colliding and slamming into itself, the impact type of thing of material creates energy, creates heat energy. But even today, like I said earlier, when you have an asteroid or a comet hit the surface of the Earth, it creates energy, heat energy. So impacts with asteroids and comets, whether it happened in our past or now or in the future. But I think the most obvious energy source that we can look at is the sun. Okay? The solar radiation. I'll look at a diagram in just a moment about that and talk about what that energy is doing and where it goes. I want you to remember that the main source for the Earth's energy that we depend upon and affects these processes is the sun, through, of course, solar radiation. That solar radiation has a major role in our hydrologic cycle, the water cycle, which, of course, deals with water. Good old wonderful water. And I'm going to say more about water in a little bit. And one of the other forces in the universe that's affecting and driving a lot of this and working with it is gravity. Gravity powers erosion. Things move downhill under the force of gravity, like big mass movement, landslides, rock slides like we've seen. So, external sources. The internal sources come from the early formation of the Earth and the subsequent chemical evolution of it, and particularly the radioactivity that's occurring inside the Earth. So radioactive elements are another source of energy in the inside of the Earth that drives something else. So specific, we'll get into later on, it has to do with plate tectonics. So those are the two main areas of this, and I want to just kind of look at some images of some of this to kind of move on. We'll come back to maybe kind of how radioactivity functions kind of simply today, and then in a subsequent class period go into it in more detail. I use this slide that Abbott uses to kind of show the early formation of our solar system. This is actually a galaxy, and as celestial material after the Big Bang coalesced under the force of gravity, and things began to collect and coalesce and become large masses, material is colliding. And in that collisional force, there's frictional heat that's produced. So in the earliest formation of our Earth, that's what happened. The inside of the Earth was warm because of that collapse. And of course, we can still have it going on today and on into the future through that. So it's not just during formation, but also now. It's a continuous evolution. This is his example, or an example of the nearest energy source, or main one, the sun. And two main gases, of course, are fueling this process. The two gases you need to remember are hydrogen and helium. This is a spectacular shot of the sun showing solar flares. And that shifts, and we get our solar flare cycles periodically, and some of that energy is bombarding the Earth. And I know we just had one recently where it disrupted some of the satellite stuff. And if your TV's not working, once in a while you call the cable company and say, oh, it's the sunspots again. Once in a while that will happen. So hydrogen, helium, simple, two simple little elements. Burning is keeping the driving mechanisms going for our planet. Kind of wild. So let's take a look at the sun in this diagram from your textbook, okay? All right. Now, like I say, most of our energy comes from the sun. When you think about the amount of energy the sun pumps out, okay, although very little of the sun's energy reaches Earth, it provides 5,300 more times energy than the Earth's interior. So most of the sun's energy goes where? Into space. We get just a little bit of it that hits us. But that little bit that hits us is nearly everything we've got. All right? The other remaining small part, 0.2%, is this internal radioactive heat that's coming out of the Earth. But I want to use this diagram to point out where some of this energy ends up. You kind of want to look at this and circle some parts and put some stars next to some things, because I will certainly ask you questions on this on the exam. All right, let's take a look at what happens here. Some of this energy, 30%, of course, is simply reflected back into space, off the clouds, off the snow, off of ice. Okay? 47% of it that hits the Earth comes in short-wave radiation, comes back and gets trapped in our atmosphere. Okay, long-wave radiation, when it comes off the surface of the Earth, is kind of trapped in the atmosphere. It's directly converted to heat, i.e. what? Global warming. And that fluctuates through time. Some of this energy is stored in another area, about 23% it says. Evaporation and precipitation gets caught up in the hydrologic cycle, and that wonder of what water does in terms of storing energy and redistributing that energy around the world, whether it be in clouds or in the oceans and so on. So it gets stored in water. We'll skip the wind. Not a lot of that really brought up into that, but let's take a look at this one. The energy that's picked up by plants and utilized in the process of photosynthesis. Okay, look how small that is. 0.023%. But look how significant it is. Look what this chart's showing us. Okay? Because of photosynthesis and the production of organic molecules and energy that gets stored, it gets stored in the plants, which eventually can end up in coal as a fossil fuel or oil. Okay? That's why I've underlined this, put a big star next to that, and said, this is small, but it's very, very significant, because another energy source we're kind of playing with is what? Going out and getting crude oil, getting gas deposits, getting coal to burn it, to create energy. And of course that does what? May or may not help with that CO2 production with global warming. So in a way, everything's tied to some kind of cycle. And where we fit in depends, and how our effect is depends on how well we interpret the data we collect on this. And we haven't come to some solid conclusion to say this is exactly what's going on. But we do know things are changing, and they seem to be warming up with this energy process. All right, the hydrologic cycle. We'll come back to this in more detail later on in the chapter on water, but I want to point it out, at least for now, because I know there's a question or two on the quizzes and maybe on the exam that deal with this cycle. And of course, in a cycle, you can start anywhere. And so what I'm going to do is kind of start over here on the surface of the ocean. And what happens due to solar radiation, the surface of the ocean, we're going to have a chemical process called evaporation take place. So moisture goes back into the atmosphere. Now, if you get enough moisture into the atmosphere, what happens? With temperature changes in the atmosphere, it will condense. And so we get clouds that form. And out of those clouds, two kinds of precipitation are shown. Rain goes back on the surface of the earth again, or it comes down in snow. Obviously, snow has to be melted. So energy has to be exchanged in that process. In the rain, when the rain hits the surface, what can happen to the rain? Well, it can land on the ocean. It can land on a lake. It can hit the surface of the earth and run off in the form of streams, i.e. floods. So again, it's all related. Or it can soak underground and become part of the groundwater process. Another really important chapter I want to talk to you about later on in the pollution conditions with that, in that case. So it's back in that cycle. And each one of these has a different kind of time rate at which it flows through there. And I'm not that concerned that you know those times, is to realize what the cycle is, and that some of it gets locked up in places for a long period of time. And I think you can see which one I want to talk about. Glaciers. I've got it starred in red. I want you to remember that when we think of fresh water on the surface of the earth, Remember, fresh water, not salty water in the oceans, but fresh water. And I'll repeat this one other time in that chapter on water, is that most of the fresh water, which we so desperately need, is what? It's locked up in glaciers. It's frozen. Okay? It's frozen. And of course, most of it's in Antarctica or it's in Greenland and all the rest of the smaller glaciers around the world. But we know with global warming and our research today, and we'll see some really wild, fun research technologies later on that we can use, but glaciers are retreating. Ice shelves are breaking off into the ocean. We'll take a look at some of these things. That changes are, again, speeding up. Whether or not it's our fault or a combination of us and nature, whatever the case is, things are changing. It has long-term things to consider. So the hydrologic cycle is something to look at and study and understand the parts of it. And again, we'll look at that in more detail on the chapter on groundwater. So what about water? What are some things we could say about water that are kind of unique within this energy bit and with the water cycle? Little cartoon up here in the top right, I'll come back to on a molecular characteristic of water. We refer to as its bipolar nature. Okay, but I'll put it all up right now again. Okay, let's take a look at the first one. Water has the highest heat capacity of any known substance on the surface of the earth except liquid ammonia. Now, to kind of look at that a different way in lay terms, it simply means that water can store energy. And how much of the earth is covered in water? Well, practically 3/4 of it, particularly in the oceans. So a lot of our solar energy can be stored in the oceans and then released at a slower rate, dissipated back into the environment. And that energy within the ocean, of course, affects how the oceanic currents occur and move. So water has the highest heat capacity, can store energy. Very important. The second thing is it has the highest latent heat of vaporization. So when it evaporates, energy can be carried into the atmosphere and then re-released when it condenses, forms clouds. So it's moving energy around within the cycles. In this case, the hydrologic cycle is going into what? Into the atmospheric cycle before it comes back down into another part of the hydrologic cycle in the form of precipitation. So in one case it gets stored, another case it gets re-released. Third characteristic about water, it has a high latent heat of fusion, again, except for liquid ammonia, which means it can absorb energy when ice melts and give off energy when it freezes. Kind of a very strange characteristic of water. Kind of a unique thing. I mean, water, think of hydrogen and oxygen. Two simple common elements have so much of an effect on the planet. And this is a statement simply about non-biology. This is not biological. We'll come to that last one. Let's take a look at the last one. It kind of sounds fancy. It says high dielectric constant, kind of a geophysical way of looking at a water molecule. But let's take a look at this molecule up here. It's too bad they didn't put the ears up on top. We could say it looks like, Mickey Mouse or something with 2 ears on it. But here is the great big oxygen molecule, large ionic size to it. And two hydrogen molecules are attached and bonded to the side, and they always go to that spot. These hydrogens are always that distance apart. And of course, hydrogen being positive, they're always 105 degrees apart. I'm not that concerned you remember this 105, but the point is this end, this bottom end of the molecule here, has more of a positive character to it electrically, whereas the upper part is more negative. So it has what we say a kind of two-sided or bipolar nature to it. It's kind of like a little bar magnet in a way, a positive end and a negative end. So when water molecules come into contact with other kinds of elements, other minerals in particular, the polarity, that electrical kind of imbalance we see in this molecule makes it a great solvent. It helps break bonds of other things and dissolve things, and those elements like sodium and potassium and magnesium and so on can actually get dissolved into the water mass itself. That's chemical processes alone, just purely chemical, involved in the erosion of material to move things through a cycle. It's a change, it's a cycle. But the other thing that's so cool about this I don't have up here is in the biological world, besides water being a solvent, it can also transport material between membranes. So nutrients you pick up when you eat or drink material is moved all around your body by the capability, this bipolar nature of the water molecule. There's more biology involved in that, but my point is that something so simple can do so much. Think about that. Remember that simplicity sometimes can answer so many questions. We found that out in the plate tectonic concept. Something as simple as just moving some plates and driving them around answered a lot of questions about earthquakes and volcanoes and the distribution of oil and gas and metal ores in the world. I want to use this diagram, kind of a cartoon, to show you this radioactivity business. If we take some isotopes, not sure if you remember your chemistry, but an isotope is where you add more neutrons to the nucleus of an atom. Okay? And if you stuff more neutrons into the nucleus of an atom, what happens is it becomes unstable. My analogy in another class one time was to talk about eating lots and lots and lots of pizza. At some point, your kind of stomach becomes unstable and you give things off, so to speak. Well, that's what happens here. We stuff more things into the nucleus, and it begins to give different kind of particles off in different ways. For example, it gives off alpha particles, beta particles, alpha particles being types of protons, beta being electrons, and gamma rays. And of course, another byproduct of this whole process, and most important, is what? Heat. Heat energy. And so this process is going on in the chemicals within the Earth. And so there's heat being formed inside the Earth, being generated, that's helping cause another situation on the outside, the crust. It has to do with the driving mechanism for plate tectonics. Let's take a look a little bit more about this radioactivity thing, since it's kind of pushed in the first chapter. When radioactive elements decay or break down, we define what's called its half-life. Let's have you write down the definition of half-life. It's the time it takes for 1/2 of the radioactive parent atom to break down, or what we say decay, into these stable daughter atoms. And here we have a chart showing that relationship in terms of half-life. Let's say we start out with 100% of radioactive material. In a certain amount of time, unit of one amount of time, half of it decays. All right? So how much of the original do I have left? How much parent material is left at this stage after one half-life? 50%. How much byproduct do I have? 50%. So what breaks down? The stable isotopes don't break down. It's the radioactive parent. So if I have 50% of that left, so in another same half-life, same amount of time, half of this breaks down. So how much original parent do I have left? 75. Or excuse me, 25%. And I have 75% daughter elements. So you keep continuing that. What happens? We keep dividing things in half and half and half and half. And theoretically, you could never do what? Reach zero, so to speak. But it's a very rapid decay in terms of this half-life time. And all different kinds of isotopes have different half-lives that we can age date rocks with. So besides the energy sources for the inside of the Earth, I'm going to throw some numbers at you periodically, and that's why I have this diagram up. I want you to remember something about this radioactive decay helps geologists age date things. Uranium lead dates, carbon-14 dates, and so on. The oldest rock, you have to remember this number now for the course, is that the oldest dated rocks on the Earth are right around 4 billion, not million, but billion with a B, 4 billion years old. Right now they think these are up in the Slave Lake region in Canada. Others argue there's a rock that's close to this up in Greenland, and the Australians are arguing there's a spot in their ancient rock terrain. But besides the argument, the oldest rocks are right around 4 billion. The Earth then, as far as when it formed and became what it was, the age of the Earth is estimated to be, by turning the clocks backwards and looking at other evidences from our solar system, particularly meteorites, is 4.6. So there's two numbers you need to remember and know from this diagram, from this slide. You need to remember that the oldest dated rocks are 4 billion, and the geologists believe the Earth is 4.6 billion years old. This table in Abbott's section talks about these specific isotopes. Okay? You do not have to memorize these isotopes. You don't have to memorize any of the numbers out of this diagram. One of the things I want to point out with this is that the percentage of these isotopes, because when you start out with parent material, you're reducing the pool of radioactive elements to becoming smaller and smaller and smaller. What's happening with time is it's declining towards zero. This figure out of your textbook, okay, that I inset into this table shows us the changes taking place. The number of radioactive isotopes was there, and it's getting smaller and smaller and smaller. Why is that there? Well, the reason for this diagram is simple. The heat-generating stuff, these isotopes, inside our planet are becoming less and less and less, which means there's less heat generated inside the Earth, which is what? The driving mechanism for plate tectonics, earthquakes and volcanoes and so on. So it all ties together. Now, maybe in your lifetime this won't have a major effect at all, but over a long time at the Earth it will. I'm going to throw one more diagram at you today. Okay, one more diagram before we're done. And it has to do with this one. It's called the rock cycle. Okay, the rock cycle. And I'll talk about this rock cycle one other time again in the semester, but I just want to give you a brief overview of what the rock cycle is and how it kind of works in this case. Now, in a cycle, I suppose you could start anywhere, and this is a pretty busy diagram to see. But I want to point out, let's say we'll start with a spot. Let's start here about this magma. Inside the Earth, in some places, liquid rock is formed. It's called magma. Now, liquid rock is less dense than solid rock, so it rises. And it starts rising up towards the surface of the Earth. Sometimes it comes out. Those are volcanoes. All right? So some of that rock comes out in volcanic form. Other ones are crystallized inside the Earth that eventually they could be exposed by uplift of the land. Whatever the case is, we've got some igneous rocks, okay, developed. And they're exposed to the air, to the wind, to the water, to the glaciers. What happens to them? They're broken down. They're going to go through physical weathering and chemical weathering and become broken into little pieces again. And so through weathering and erosion and transport and deposition, the particles that are eroded we define as sediments. Now the rivers, the wind, the glaciers move these things and dump them somewhere. So the sediments now get buried, compacted, re-cemented, and boom, we have a new kind of rock called a sedimentary rock. Things that form at beaches or in deltas or in the deep sea or in the bottom of lakes and the bottom of rivers, as just to name a few, are created. Well, you know, through uplift, I could bring those rocks right back to the surface and bash them apart and start all over. It's a cycle. Anywhere in the cycle can part. Or I could bury them deeper and deeper and deeper and get deeper in the earth, and the heat goes up and the pressure goes up, and I can squeeze them, and I can change them. I can recrystallize them in the solid state, realign their shapes. Well, if I do that, I create a third category of rocks, in the bottom right here, called metamorphic rocks, meaning a change of form, because they underwent all this heat and pressure changes. Well, I could uplift that and recycle it back in too. Or I could do what? I could jack the temperature up so high, what happens? I melt them. And where am I in my cycle? I'm back here to where I started. So in these systems, okay, in this relationship, some of these areas are involved in our environmental process, particularly volcanism or uplift that has earthquakes associated with it. So we'll come back to parts of this off and on as we look at this stuff throughout the semester. I know that in subsequent chapters we're going to look at minerals and then rocks and then volcanoes, kind of lead in some of the background information, and finally we will go to, earthquake activity. and volcanic activity that's part of the natural hazards. So I think that's it for today, and we'll see you next time. Okay? If you have any questions, feel free to hang out or contact me by email if you're doing it through distance learning.